Hello everybody, Spider Pilot 747 here, and today we are going to be looking at one-dimensional collisions in classical mechanics, and specifically collision between two bodies. Some of the important things that we will be looking at is how to find the final velocities of two objects after a collision, as well as how to find the energy loss. We will be looking at both elastic and inelastic collisions. We will be starting with inelastic collisions, which essentially means that when two bodies, such as these two spheres, collide with one another, the final product of this collision is going to be these two spheres moving at the same velocity. So one of the fundamental principles for inelastic collisions in order to solve what this final velocity will be is the law of conservation of momentum. The law of conservation of momentum suggests that the momentum of a system, such as these two interacting objects, will be conserved through any processes inside of the system in the absence of an external force or external influence. So in other words, if we have mass 1 here and mass 2 here, with velocity 1 here and velocity 2 here, then the momentum, if we sum the momentum of both of these objects, then it should be the same as the momentum of this, where we have v equals question mark, and we have a total mass of m1 plus m2. Now the interesting thing about inelastic collisions is that you can use this law of conservation of momentum through the one-dimensional, two-dimensional, or three-dimensional, and it'll pretty much work for all of those very simply. Inelastic collisions are extremely simple in any dimensional sense, and that's because you have the same number of unknowns as you have equations simply using the conservation of momentum. So let's write out the conservation of momentum for two colliding bodies. So we have m1 v1, and we'll do this generally with vectors, plus m2 v2 equals m1 plus m2 times v prime. And this is the law of conservation of momentum. We have the momentum for body 1, we have the momentum for body 2, and we have the momentum of the final product. So as we can see here, the final velocity will be very easy to solve. So for any nth dimensional system, you can see here we have these two as knowns, and I'll put a check mark above what we know. So we know these two masses, so by default we know these two masses. We know what the initial conditions are, the initial velocities, and what we don't know, and I'll circle it, is this velocity. That's what we want to find. So as you can see, if we have a three-dimensional system, we will have three of these equations because we will have an x, y, and z for velocity 1, an x, y, and z for velocity 2, and we will have three unknowns as we will have an x, y, and z for this final velocity. But we're going to stick with one-dimensional for now, so we'll convert these vectors into just being a scalar one-dimensional representation. So what we will have is we will have m1 v1 plus m2 v2 equals m1 plus m2 v prime, and therefore we find that v prime equals m1 v1 plus m2 v2 over m1 plus m2. And that's all it is. So this velocity is going to be for both of these masses after the collision has occurred. And now what we can do is we can take a look at how much energy we lose. So we have kinetic energy. And it looks like I'm getting low on disk space here, so hopefully I can wrap this up quick. So for kinetic energy, we have 1/2 mv squared. So if we take kinetic energy and we take the kinetic energy before the collision and after the collision, we will have the following. So this E1, that's our energy before collision, we have this E2, which is after collision. So now if we take the difference between these two, we will find how much energy is actually lost in this collision. And we can substitute our known for V prime now to figure what that is. So E1 minus E2 equals M1V1 plus M2V2 over M1 plus M2 squared. So we're taking this and we're simplifying it a little. So therefore, our loss of kinetic energy is equal to M1V1 squared plus M2V2 squared minus 1 over M1 plus M2 M1V1 squared plus 2 M1 M2 V1 V2 plus M2 V2 squared. So this is what our loss of kinetic energy is, and in general you will find that this is a positive number because we can't gain energy from a collision. And one thing that we can use to check this equation is the units. So we see here we have units of joules, or units of energy, kilogram times meters per second squared, or kilograms times meters squared per second squared, in other words, Newton meters. Same units there. And here we have kilograms squared, meters squared per second squared over here, but we are also dividing that by kilograms, so the units check. So that's what your loss of energy is going to be from an inelastic collision. And so we can see that an inelastic collision is not perfect. We lose energy because this will be a positive number. We do, in fact, lose energy from an inelastic collision, and that's mostly being lost to noise, friction, heat generation, etc. So an inelastic collision is actually not perfect. So next we're going to be taking a look at a case where we do have a perfect collision, where we have this energy conservation as well. But first we're going to take a look at a little bit of how we can derive the mathematics behind such a perfect collision. So essentially, we know that momentum is the integral of forces with respect to time. And that's where we kind of get the law of conservation of momentum, is the fact that if we have no forces, no external forces acting on a system, then this is going to be equal to constant. Another way of writing this would be that the momentum at one point, we'll call momentum h, momentum at one point, plus an impulse, which is going to be your force over some time, is equal to some new momentum. So momentum is only going to change if you have an external force acting on your system. Energy is the integration of a force along a distance. So a dot product of some force, we can take this even as being vector, but in this case we're going to be doing the scalar form of it. So we know that from Newton's second law, F equals m times a. And acceleration is equal to the differential of velocity with respect to time. Another way of writing this, acceleration should also be equal to dv by dx times dx by dt, or in this case we have an s. So our energy for kinetic energy is equal to the integration of dv dx dx by dt dot ds, or in this case, dot dx. If we simplify this, we have this dx down here, we have this dx up here, we get this is equal to the integral of dx by dt, which is just v, times dv, which, integrating this, once we realize that we forgot to put the mass in there, what we get is m times 1/2 v squared from some position 1 to position 2. So in other words, our kinetic energy E equals 1/2 mv squared. But we can see a similarity here, where if we have momentum, we have a force multiplied by differential time, but in energy, we also have a force. The difference being that energy is going to be integrating this force along a distance, whereas momentum is integrating it over some time. So if we take this energy, and we say that energy is conserved, then we already know that if there's no external force, momentum must be conserved. We essentially start to see that our momentum, which is going to be defined as mv, which is equivalent to ma dt, or m dv by dt dt. So kind of what we start to see here, since we have this F equals ma, we can start to see that ma dt have a bit of a common factor there. So essentially, what you see here is that energy is going to be more of an integrated form of momentum. So that if we differentiate our energy with respect to dx by dt, then we essentially have, I'll do this one in green, f dot dx and since we're differentiating with respect to dx by dt, differential of this with respect to the differential of this. And so essentially what we see here is that our energy equation is directly related to our momentum equation by differentiating. So in other words, if we have energy on this axis and we have velocity on this axis, if energy is constant with respect to velocity, or in other words, energy is conserved, then automatically this slope is going to be 0, so our momentum also has to be conserved. In other words, if energy is conserved, so too is momentum. So basically, if we have energy conservation, we can pretty much assume that we have momentum conservation. However, since this is differentiating to get momentum, it does not work the same way around, as we can see in the following diagram. So if we have momentum here and velocity here, if we integrate this, we will find that our energy is in fact not constant. So in other words, if we have conservation of energy, we have conservation of momentum. But if we have conservation of momentum, we do not necessarily have conservation of energy. And this is where elastic collisions and inelastic collisions start to differ, because in elastic collisions we do have a constant energy. This relationship is going to significantly help us, specifically this relationship here. I would like to again point out that this is just conjecture. There's no numbers to this. And some of the mathematical operations to this might be a little bit dodgy. This is simply showing kind of how it works, so that you can get an idea of how these are related. So next we are going to look at elastic collisions. Now, elastic collisions are collisions in which energy is conserved. So essentially, if we have two objects moving towards one another, then they collide, we get a case where we have two objects which may not have the same velocity. They're not moving together. And they could be moving in the same direction. In this case, I think it'd probably be more likely if there's the same mass, then these would start moving in the opposite direction. But energy is conserved, so our total kinetic energy here is the same as the total kinetic energy here. And this complicates our equations a little bit, because no more can we rely simply on the conservation of momentum, because we see here that these are not moving at the same velocity. So we will have two unknowns with only one equation from the momentum conservation. So let's write that out. We have m1 v1 plus m2 v2 equals m1 v1 prime, is this one, plus m2 v2 prime. And these do not need to be in the same direction. So as you can see, we have known, 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 known. These two masses are known, but these two velocities are unknown, and we have only one equation. So in order to solve an elastic collision, we need to have one other equation at least. So let's look at energy. So as we just said, energy is conserved. And since energy is conserved, that implies momentum is conserved, so we're justified in using the momentum conservation principles. So let's take a look at energy. 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. And just to simplify things, we'll take out these halves, and we have our second equation, m1 v1 squared plus m2 v2 squared equals m1 v1 prime squared plus m2 v2 prime squared. So now we have two equations. Call this equation 1 and this equation 2. We have two equations. We know this, we know this, we know this and this, we know this, we know this, and we have these two unknowns still. So two equations with two unknowns. And now we can solve for these two velocities. So if we go from equation 1, we'll get an expression of v2 prime. We'll get an expression of v1 prime in terms of v2 prime. So we'll see that m1 v1, this will be from the first one, plus m2 v2 minus m2 v2 prime, all divided by m1, equals v1 prime. So now we can plug this whole big equation here into here, and simply solve for v2 prime. We'll have a quadratic. We will find that we get a quadratic equation out of this. So let's continue with this. m1v1 squared. I might just actually speed this up to the end, and then you can look at the pretty maths. v2 prime there. That should be v2 prime there. Maybe a bit of a clerical error. Which means this should also be v2 prime. Sorry about that. This should be m2 squared. My apologies. Squared. You can always check the units to make sure that's correct. Units in any equation should be homogeneous, so now this all equals 0, which gives us a basic form of a quadratic equation. So now using the quadratic formula, we get this is equal to negative b and somewhere through my math I forgot a 2, so please include that. I missed the 2 right there. A lot of numbers. There's a lot of variables in this equation, so it's very easy to misplace 1 or 2. In this case, 2. And once again, that should be carried over into there. Missed it up in here too. So one thing that we notice is we can pull a 2 out of everything right off the bat. So we have a 4 here. We have essentially a 4 here if we take a factor of 2, and we have 2's right there. So this equals This is a lot of stuff. Now let's collect like terms. We have this one here, which stands out with this one here. So we'll cross these two out. We have this term here and this term here, which cancels with that. We have this term and this term, which also cancel out. Now this may not look like much at first, but let's take a look at this in greater detail. V1 minus V2 squared results in this expression. And since it's a square root, this tells us or just V2. Now we can note that if the second velocity of V2 is equal to V2, the initial condition, then it's inconsistent. We know that in a collision the velocity has to change, and in addition to that we know that V2 prime cannot be equal to V2 because M2 is not infinite. If M2 were infinite, then it might be possible that it would approach V2, however it would never actually achieve the same velocity. So this would be either consistent with no collision happening at all, or with an infinitely heavy mass for object 2. However, this we can generally discard and take this one instead, because we can see if M2 goes to infinity, this will drop out to 0, this will go to 1, we'll get V2 anyway. So this is overall the better solution. It captures both possibilities. So essentially V2 prime equals 2m1 v1 divided by m1 plus m2 plus m2 minus m1 divided by m1 plus m2 times v2. And now, based on our conservation of momentum that we had written earlier, we had v1 prime equals m1 v1 plus m2 v2 minus m2 v2 prime, all divided by m1. So now we have an expression for v2 prime which we can plug in. So we can see a common denominator starting to emerge. So we're going to use that to our advantage. Sorry, V2 there. Finally, we can collect these like terms. We have minus 2v1 m2, we have plus v1 m2, so that'll just become a negative. We have this ugly thing and this ugly thing. These two will cross out. therefore, overall, we get v1 prime for an elastic collision equals m1 minus m2 over m1 plus m2 v1 plus 2m2 divided by m1 plus m2 v2. And we get v2 prime for an elastic collision equals 2m1 over m1 plus m2 v1 plus m2 minus m1 over m1 plus m2 v2. So these are your equations for elastic collisions. As you can see, it's a very difficult process to reach these. If you go to 2 dimensions, it gets even more difficult. 3 dimensions is even more difficult, but if you can do 2 dimensions, you can do 3 dimensions. And I'm not going to do that in this video, however, I might upload a video later where we derive the 2-dimensional equations if there's sufficient interest. So that's the basics of 1-dimensional collisions. As you can see, a little bit difficult to derive, but these equations are very friendly to use. And you can kind of see what happens. For example, if m1 goes towards infinity, then we start to get v2 being equal to 2 times the initial v1, and we get v1 pretty much staying constant. So, you know, there's some interesting things that you can see as different variables do different things. So this was just 1-dimensional. However, the inelastic result is fairly easy to derive for 2-dimensional and 3-dimensional. The elastic ones tend to be much more difficult. So once again, just to recap, elastic is basically conservation of energy plus conservation of momentum, and inelastic is just conservation of momentum. I'm Spider Pilot 747, and I guess have a great weekend.